Hello, this session 3 focuses on 3 permutations of confined and unconfined domains that are commonly used in Anaqsim. You've got confined, unconfined, and then a hybrid of the two. And I will, in addition, talk about the nature of confined domains, which generates linear boundary condition equations, versus unconfined domains, which tend to generate nonlinear boundary condition equations, and what some of the consequences of that are. Also talk about how Anaqsim handles unconfined domains where the head falls to or below the base, thus drying it out or dewatering it. And then I'll talk about different approaches for handling an unconfined aquifer with a sloping base. These 5 domain types are what are available in Anaqsim. And the first 3, unconfined, confined, and a hybrid of the two, are the subject of this video session. The latter 2 here are fresh salt interface domains for coastal aquifer modeling, and those are the subject of a later video. In Anaqsim, you can mix any of these 5 domain types in a single layer, which is quite handy and flexible. Confined domains are the same as a fixed transmissivity domain in Anaqsim, and these should be used when your transmissivity is fairly consistent over the area of a domain. And that means that it's not just for confined domains, being, layers that are confined by an aquitard above. They can also be used for unconfined domains that have a fairly consistent transmissivity despite possibly sloping base. So that's another application of these confined domains, and it would be nicer if they were called fixed transmissivity domains so that you wouldn't hesitate to use them in an unconfined situation. But we're stuck with the terminology confined. That's widely accepted. When you're using a confined domain, the storage parameter in a transient model can be either specific storage, which is S sub S, and that has units of 1 over length, or it could be storativity, which is specific storage times the saturated thickness B, and that is dimensionless. So either of those can be your input storage parameter in this case. The inputs include the bottom elevation and the top elevation for the domain, and the saturated thickness, B, is just the difference in those two numbers. If we look at the last point here in this equation, the potential to head relationship is linear. And that helps in the solution of the boundary condition equations. Whenever you have confined domains being the only ones involved in a boundary condition equation, the program does not need to iterate to home in on the solution. It can get it in the first iteration because of that linearity. Unconfined domains should be used when the water table occurs within the domain itself, and never when the water table doesn't occur within the domain itself. The transmissivity is computed here as the horizontal hydraulic conductivity times the saturated thickness, which is the head minus the base elevation, or H when you're measuring it from the base like this. This is very useful when you have features like wells or drains or something that will alter the saturated thickness in a very local way. And when you use an unconfined domain, the base of the aquifer is assumed horizontal, but the saturated thickness varies with the head. In an unconfined transient model, the storage parameter that's used is specific yield, this S sub y, which is dimensionless. And the potential to head relationship is nonlinear, as shown in this equation. The potential is proportional to head squared. So these boundary condition equations will typically require iteration to home in on the solution. There's a hybrid confined/unconfined domain that you can use when your domain may be confined in some part of its extent and unconfined in other parts. And whether it's going to be treated as confined or unconfined depends on the head relative to the top elevation. When the head exceeds or is equal to the top elevation, it's treated as confined. And when it is lower than the top elevation, it's treated as unconfined. And that transition where it occurs, say like this spot here, you don't have to know that beforehand. The model can figure out where that will occur, and it automatically uses confined storage parameters and mathematics in the confined area and unconfined in the unconfined area. It's a very nice feature that is possible with analytic elements, but not with other kinds of methods. When you're in the confined mode with the head above the top, the program will use storativity for the storage parameter, and when you're in the unconfined, it'll use specific yield for that. Just some general guidance about domain property input. When you're specifying levels, generally you would start with 1 for the topmost level and increase the level number as you go deeper in multi-layer areas. But that sequence of numbers doesn't have to be continuous. You could go from 1 to 3 to 4 and have gaps. And that can be handy when you're assigning level numbers so that you can make contour plots of a series of domains that make sense. Like, let's say you have 2 levels in one part of your model and 4 in another. You may want to call the lower of the 2 levels in the 2-level area level 3 because it lines up across from level 3 in the 4-layer area. So when you apply boundary conditions to the top and bottom of a model, like recharge, for example, that is always going to be applied at the topmost layer. For example, if your uppermost layer is level 2, that's where the recharge would be applied if you didn't have a level 1. And the same is true for bottom boundary conditions. If you apply the leakage rate out the bottom, it would apply to the level present at any given location, which has the highest level number. When you're inputting hydraulic conductivities, the Ks, K1 and K2 are in the plane of the domain, typically horizontal, and K3 is normal to the plane of the domain, typically vertical. And when you do anisotropic domains, K1 and K2 can have different numbers, and at that point, if you're doing that, then there's an angle that you specify, which is the direction of K1 relative to the positive x-axis. So your anisotropy in the plane of the domain is totally flexible in terms of the ratio of the 2 numbers and the direction. So that you can easily switch between different domain types, like confined and unconfined and so on, there is some potentially superfluous input in the input that's required, because you need to input data for all possibilities, confined, unconfined, and so on. So when you have an unconfined model, for example, you'll still have to put in a number for the confined storativity, S. The model will only use the specific yield storage number, S sub y, but you still have to put in values for everything. And an unconfined domain, for example, doesn't use the top elevation, but you have to put it in just in case you switch it to a confined mode later on. But the practical value of that is that you often want to start your modeling model building exercise with confined domains, because these are really simple and they behave very well. They're linear and they never go dry and so on. So you might want to start building your model using confined domains, and once you get it kind of tuned and running reasonably, then switch it to unconfined where appropriate. There's a parameter called average head that you'll see in the input tables, domain input tables, and that should be kind of the typical expected head in the area of the domain. And it doesn't have to be exactly the average. It just has to be in the ballpark, and it won't affect the model result if you bump it up and down a bit in the typical range. What it does, it determines a constant in the potential equation, and in transient runs, there's the possibility that you might use it as the initial head at the start of the simulation everywhere in the domain. That's one option. Here's an example to illustrate how to use confined and unconfined domains in a multi-level model. This is a model of an unconfined aquifer, but that one aquifer has been subdivided into 4 different levels to account for three-dimensional flow near some partially penetrating features of a dewatering scheme. And I'll point that out right here. The drawdowns here are due to a line element boundary at the margins of a pit, actually. So there's extraction along lines perpendicular to the section at these 2 points here. And you can see these are the head profiles in the 4 different levels of the model. This profile only shows the upper 3 elevation-wise. The upper level, you'd use an unconfined domain, and that's because it's the topmost level in the model and the water table occurs within that elevation range. The lowest level here, level 3, should be designated a confined or fixed transmissivity domain because its transmissivity is fixed. The water table never penetrates as deep as this layer, so the saturated thickness is always going to be the elevation difference from the top to its bottom. So that is appropriate for confined. Level 2 here is a good candidate for the hybrid confined and unconfined type of domain. Most of its area, the water table is above the top, so you'd want to have it behave like a confined layer, fixed transmissivity using this saturated thickness. And over here, right near the dewatering system and here, the water table does occur within this, and it does reduce the saturated thickness near those features. So the confined/unconfined hybrid type domain will do just what you want. Make it behave unconfined right near the dewatering features that pull the water table down that deep, but confined elsewhere. Just a caution not to use unconfined domains in anything but the topmost domain. For example, you may be tempted to call level 2 unconfined, since the water table does occur within it in certain areas. But if you did that, the model would compute saturated thickness in level 2, say where my cursor is, as the difference between the base elevation here and the water table all the way up here. So it would give you an erroneous saturated thickness, like 2.5, 3 times as much as it should. So generally, the unconfined is reserved just for the topmost layer. This profile that we were just looking at has the uppermost level 1 as an unconfined domain, and you can see that right here, right near the dewatering system, in both these places, the heads have been pulled down below the base of level 1, and that would essentially dewater or dry out the uppermost level. Anaqsim has implemented a scheme to handle this that allows the model to still converge and converge on a reasonable solution. In these dewatered areas, the level 1 domain, the unconfined domain, switches to a very thin confined domain with a small transmissivity and saturated thickness. And that allows the model to continue on towards convergence without that skinny domain conducting significant amount of flow and impacting the entire model. And similar schemes have been implemented in ModFlow, where you have the same issue with domains that can dry out. Here's how this works in Anaqsim. There is a minimum saturated thickness in an unconfined domain, and that is computed as the saturated thickness at the average head times a factor that we'll call the almost dry fraction, ADF. And by default, that is 0.01 or 1/100th. So this minimum saturated thickness by default is 1/100th of the saturated thickness at the average head. And again, that's specified in the domain input. And this almost dry fraction constant or fraction is input in the solve settings. And I say it defaults to 0.01, but you could make it lower or higher. So when you get a solution this way, it's as though there's this very skinny confined domain in those areas where the head is at or below the base of the unconfined domain. And you make it skinny and thin so that the amount of flow that's going horizontally in those regions is insignificant compared to other horizontal flows in the model. So it doesn't really affect your solution much, but it lets your solution converge. The heads that result are unrealistic and should be ignored. And in the contouring algorithm, when you're contouring heads, the plot areas where the heads are at or below the base will be blank. No contours will be drawn there. Confined domains generate linear equations, meaning that the discharge potential is directly proportional to head, whereas unconfined generate equations where discharge potential is related linearly to head squared, so it's nonlinear. And it's sometimes more stable and easier to deal with confined domains instead of unconfined domains, although these can be quite stable and behave just fine. But with unconfined domains, you have some non-linearity in the boundary conditions, which means you have to iterate to find the solution, and it generally does converge within 4 or 5 iterations. But with confined, it'll probably converge in the first iteration if everything is confined in your model. And I often start modeling with confined domains everywhere just to get it all behaving fine, and then I introduce unconfined or fresh salt interface domains as I list here. When you have an unconfined aquifer that has a sloping base, and especially if the slope of that base is fairly large compared to the saturated thickness of the unconfined aquifer, then that's a difficult problem for any software, including analytic element programs. So you have a few options. The first would be to create a series of unconfined domains that kind of stair-step the base elevation down following the slope of the base of the aquifer. And that can work reasonably well if you don't have to have too many steps, and again, if the drop in base elevation is not on the same magnitude as the saturated thickness. What can cause problems there is that you get the aquifer or the domain drying out near the lip of one of these stair steps, and that can be a difficulty with convergence. So an alternative would be to use a series of confined domains that approximate the distribution of saturated thickness and transmissivity reasonably well. Remember, these domains are not accounting for the vertical resistance to flow, just horizontal. So if you do step 2 in a reasonable way, it's a good approximation. You could also do a hybrid here where you do step 2 for most of your model, but right near a feature like a pumping well that's pulling the saturated thickness down significantly, you could just embed a local unconfined domain right in the near vicinity of that well. And I have adopted that option quite a bit. That's quite useful. Here is one reference alluded to in some of the later slides in this video, and it's a paper that I published in 2018. It came out in the journal Groundwater, and it covers the technique for modeling the dewatered domains, unconfined domains, where the head drops to the base, and that may prove useful for you, and there's a link there.